Thank you for nice introduction, and it's a really great honor to be invited in this nice seminar. And I'm Mi-kyung Shin at Sungkyunkwan University, and today I would like to introduce my recent works and basically the tissue adhesive materials. I'm developing the tissue adhesive hydrogel or other polymer-based materials, so I will introduce the many material formulation for the suturist, bioelectronics, and peripheral nerve repair. Before starting my talk, I will introduce what kind of materials we can develop in my lab. So the first material is the adhesive polymer material. So you can see here, so we can develop the adhesive materials which can adhere the many different organs: stomach, intestine, liver, cardiac tissue, and blood vessels. So recently, we have developed this film type materials for the blood vessel sealing. Second material is the injectable and conductive hydrogels. The hydrogel materials has the very tissue mimetic, the mechanical modulus, so we can use this material for the tissue regeneration, and we can also provide some the electrical conductivity to the hydrogels, which can be effective as the bioelectrode by itself. So using this hydrogels, we can print tissue, or we can also we can also print this hydrogel on tissue, and we use these hydrogels after the filling to the tissue defect for combining with bioelectronic device. And we recently have the integrated this hydrogel materials and bioelectronic device for the closed loop, the robot assisted system, and that will be first topic for my talk. So using this adhesive material or injectable materials, we can achieve the peripheral nerve repair like here, or we can also develop the therapeutic platform for the cardiovascular disease. Let's move to the next slide. This slide shows my research motivation. So for developing and designing the new adhesive materials, we are mimicking the nature adhesion phenomena. You can see the many examples are here. The first example is the marine mussels. Marine mussels have their own visor thread, and this thread is composed of the cortical moieties. This cortical moieties has the benzene ring and hydroxy group. Because of this functional group, they can show the underwater adhesion. So as you know, the marine mussels can adhere under the water on the many different substrates like organic or inorganic substrates. So if we use these cortical functionalized materials, we can coat the surfaces like organic or inorganic in material independent manner. Other creatures like sandcastle worm or barnacle, they are also secreting some of the polymeric and sticky materials for their life. And the other oceans creatures are here, the tunicates. Tunicates have also the chemical moieties, which is called the gallor. The gallor has the 3-hydroxy group and benzene ring. That is only difference the 1 hydroxy group compared to the cortical. So these gallor moieties have been known as that they are having the higher the water resistant adhesion properties compared to the cortical. So in our lab, we are using the both materials for getting the underwater adhesion for bioelectronics and other tissue repairing materials. So basically, we conjugate the cortical or gallor, which are called the polyphenol. The polyphenol can be tethered on the natural polymer, chitosan, arginate, and hyaluronic acid. So these natural polymers can be prepared after the extraction of the natural organism. And then this tannic acid molecule is one of the plant extracts. And they are having a lot of cortical and gallor in the chemical structure. So because of that, tannic acid has also the high and strong adhesion under the water. So using this polymer material, we can make the film type material after the dehydration, and we can also prepare this hydrogel material and micro bead type material. So using this different formulation, we can achieve the drug delivery system or the simple glue system and bioelectronic system and so on. Why we need to use the cuticle or galur materials? This is the chemical mechanism involved in their chemistry. First of all, the galur or cuticle can be easily oxidized to form the quinone foam. The quinone is highly unstable, so they can cross-link, like here, they can cross-link by themselves to form the covalent bonds. So using this covalent bond, we can make the hydrogel via the cross-linking. And then they are also having the multiple non-covalent bonds, like hydrogen bonding and pi-pi stacking interaction and metal coordination. So using these non-covalent bonds, we can cut easily this galur or cuticle polymer materials on any substrate. So these substrates can be the electronic device, or this surface can be simply biological tissue. So that is the adhesion mechanism involved in the cuticle or galur chemistry. So this video shows one of the glue example we have developed. So this glue, you can see that is the highly stable underwater, and then they are having the reversible adhesion properties. So in this glue, there is the epigallocatechin gallate, which is one of the green tea extract molecules. So when we mix this EGCG and the synthetic polymer, the polyethylene glycol, we can generate this glue spontaneously. So as you know, our body has a lot of water. So this water-resistant adhesion property of our glue is very important for the stable and the fixation properties of other material or device as well. During my PhD and postdoc works, so I use the cuticle molecules for conjugating onto the chitosan molecule, and then we simply dissolve this chitosan cuticle and the drop on the needle surfaces that will be the inorganic substrate. After that, we can get the film type material. This cylindrical type of the films is a solid, but after the blood contacting, they can be formed as the adhesive hydrogel. So this hydrogel can be fixed on the tissues. So even after injection and even after the withdrawal needle, they are showing the hemostatic effect, that is stopping the bleeding. So this needle was the first hemostatic needles in the world. So using the needles, we can achieve the stopping the bleeding from the diabetic patients or the chronically advanced cancer patients and so on. So after that works, we are thinking about if we have the strongly adhesive polymers like the galur conjugated one, we can get the much better adhesion for the tissue sealing. So my graduate students synthesized the chitosan galur, and then we also fabricate the film type material, and then we checked the adhesive strength of the film material. So you can see here the high concentration of the galur moieties can achieve the better adhesive strength. So using the film material, we would like to seal the elastic and very thin layer. For example, the diaphragm. The diaphragm membrane is located on the bottom of the lung. So we made the ex vivo model, like the artificial lung model, and then we just puncture using the needles. At that time, the air is full out, and then you can see the pressure value was decreased. And then we use the film adhesive film for sealing this hole. That is the experiment here. So after applying this transparent film on the pore, and then the pressure is immediately increased up. So as you can see here, so if we use this self-sealed membrane, it's useful for the sealing the tissue defect. Based on this research, we recently developed the blood vessel sealing material using the two different polymers. The first one is the chitosan galor as the adhesive polymer, and the second one is the chitosan boronic acid as an elastic polymer for the supporting mechanical modulus of this chitosan galor. So when you transact the blood vessels, we need to do stirring for sealing, stable sealing of the blood vessels. But if we use this film materials, we can support the stirs for the stable sealing, like here. So firstly, we apply the adhesive materials on the blood vessels, and we secondly apply the elastic film for the stable sealing of the blood vessels. So actually, we wanna check the no suture method using this film, but it has not enough adhesion properties for the no suture method. So we simply check how many sutures we need for the stable sealing plus film. So as you can see here, the stirring number is 10. It's showing the stable sealing of the blood vessels. But if we use the film material, we can decrease the stir number because of this augmentation by our adhesive film. So that is one of the vascular anastomosis method using the adhesive film material. This topic is more the main topic in my talk. So recently, we are using our adhesive polymers for the stable fixation of the implantable bioelectronics. So as you guys all know, these implantable bioelectronics are very attractive for the stimulating to our tissue or recording of our electrophysiological signals. We already have electroactive tissue such as the brain, or nerve, or peripheral nerve, or muscle and cardiac tissue. Many researchers have developed a lot of bioelectronics with stretchability and softness. They wanna match the mechanical modulus of that material to our body, right? But that has a still steep material, I think. So we can change that material, but in our lab, it's more focusing on these interfacing materials. So if we change the interfaces with the hydrogel material, that hydrogel can have the matching to the tissue, and they can have a role for the fixation of the electronics if we use the adhesive hydrogel as an interfacing layer. And then that hydrogel can have the electrical conductivity, so we can have a effect for the coupling in between the electronics and the tissues. So that is the reason why we are using the hydrogel biointerfaces in between the electronics and tissue. So for that, we simply use this film type material. So simply we dissolve all polymers as a solution and then drop the electronic surfaces and then simply dry it. That's all. So after the film formation, we attach that electronics on the tissue. This film can be changed to the adhesive hydrogels, and then our electronic device is easily fixed on the tissue using this adhesiveness of the hydrogels. So usually we use the arginated catechol or arginated boronic acid and the chitosan catechol. This type of the materials can have adhesiveness for the bioelectronics, and let me show you the details in the next presentations. So today's topic is actually three. The first one and second one is the application on the peripheral nerve and the muscle regeneration, and then the other topic is just the injectable and conductive hydrogel, but that is on the wearable electronics. So let's just start to have the injectable biomaterials. So actually the injectable and conductive biomaterials are already used for the tissue scaffold. What kind of tissues? Such as cardiac tissue, neuron, nerve tissue, or muscle tissue, and so on. So if we give some conductive environment surrounding these tissues, then material can trigger their differentiation or their regeneration. Our research idea is if we use this conductive material for the filling and implanting to the tissue defect, we can get much better rehabilitation for this patient. Actually, if we use only this material, it is not effective. But if we combine with the typical or the advanced bioelectronics device, we can get this immediate rehabilitation. That is our research idea. In my postdoc work, we have developed many conductive hydrogel based on the hyaluronic acid. The hyaluronic acid is the representative biocompatible polymer, so I think you already heard about that. That is the representative filler material into our skin. So if we made this hyaluronic acid with the photocross-Lincoln moiety here and Galler moiety here, this Galler has a role for the metal reduction. So by this, the Galler reduction capability of from the silver ion to the silver nanoparticle, we can get this hydrogel, the conductive hydrogel. Also, this hydrogel has the granular form, the microgel, for the better injectability. So using this hydrogel, we can print it and we can feel this hydrogel in the gap between the two muscles. Even though we stimulate only one muscle, you can see the other muscle tissue have also, have also the same contraction effect. So that means our material can transfer their electrophysiological signals in between the tissues. So, but these silver nanoparticles has a very high toxicity in our body. So we would like to change in this silver nanoparticle to more biocompatible metal systems. We choose the gold nanoparticles. So for designing this hydrogel, the injectable tissue interfacing and conductive hydrogels, we also use the hyaluronic acid modified with the phenylborate functional groups. This phenylborate functional groups is highly unique for the multiple cross-linking of the polymers. So you can see here, these phenylborate functional groups can form the covalent bonds, which is called the biphenyl links, and they can have multiple hydrogen bonds, and they can have also here the metal coordination with the gold ion. During the formation of this biphenyl link, the gold ion is spontaneously reduced as the gold nanoparticle system. So we found this chemistry, and then we also check the phenylborate has the adhesiveness on the nerve tissue, and this simulation is also showing that these biphenyl bonds can be rearranged during the injection. What is the meaning that? The rearrangement of these covalent bonds can cause the mechanically durable hydrogels. What is the difference of the typical hydrogel system is here. So typical hydrogel has the CC bond, the covalent bonds, but that type of the covalent bonds can be easily broken against the mechanical stress. But our hydrogel has a biphenyl and that can be rearranged against the mechanical stress. So our hydrogel has the mechanical toughness compared to the conventional hydrogel systems. So using these hydrogels, we would like to demonstrate these full systems. So our hydrogel is injectable and they are still conductive by the golden nanoparticles. And then we can fill this hydrogel into the tissue defect, for example, like muscle tissues. Without any device, they can cause the enhanced muscle regeneration actually, but that is the long-term scale regeneration. So we would like to check the immediate rehabilitation, not regeneration, but immediate rehabilitation can be achieved by combining with the bioelectronic device. So for here, we interfaces our hydrogel between the electronics and tissue, and we also fill our hydrogels for the easy transferring electrophysiological signals for the muscle-to-muscle tissues. And then we also connect this full system to the robotic arm for the supporting the gait of the animals. So let me show you the full system. Next slide. The first one, we want to check the transferring capacity of our hydrogel about the EMG. So when we fill our hydrogel by stacking the hydrogel filament between the muscle tissue, so after the filling this hydrogel into the defect area, they are showing the recovery of the EMG amplitude compared to the uninjured muscle tissues. So that means our hydrogel can connect electrically between the tissue area. So based on this result, we want to check the combining effect with the bioelectronics. Before that, we also check the muscle regeneration capability. So after the filling our hydrogel, we check the repaired myofiber. So as you can see here, at the second week point, we see the enhanced muscle regeneration compared to the typical gelatin-based material. So that means the conductive material can accelerate the myofiber regeneration in the muscle injury model. After that, we also implant this soft electrode for the nerve stimulation. So as you know, the nerve stimulation can evoke the muscle signal, right? So we use the soft electrodes for the stimulation on the muscle and recording for the muscle tissues. And we also fill our hydrogels on the defect region. So in vivo system, we prepare this animal model with severe muscle injury. So we fill our hydrogel like here for the regeneration and then for transferring electrophysiological signals in between muscle tissues. And we also implant the soft electrodes as I mentioned it in previous slide. And then we also interface with our hydrogel for between this electrode and tissue. And we also implant the same electrode underneath the muscle. And then when we stimulate the nerve tissue, that can evoke the muscle signal. At the same time, the robotic arm can be activated for the supporting the gait of these animals. That is our full system. So you can see this video without any stimulation. The rat has the gait failure. So the robotic arm cannot work at all for the supporting this gait. But with the peripheral nerve stimulation, the robotic arm can be activated by the evoked EMG signals, and they can raise up the foot of these animals. So this can be the initial stage of our platform, but we can develop for the advanced rehabilitation system using hydrogel and bioelectronics. Okay, so the next topic is another injectable and conductive hydrogels. So comparing to the previous injectable and conductive hydrogel, actually that material has more conductivity, has more conductivity, but we also parallelly developed this hydrogel for with the different morphology and different characteristics. So our idea is we can make the granular structures of the hydrogel for better injectability. So this granules has the micro size diameter, and they are having the core shell structure inspired by the basil seed. So that seed has the solid core, and they are having the soft shell for their I'm not sure why they have the core shell structure, but basil seed has that structure. So we are mimicking the basil seed. So we use the hyaluronic acid core as the granule molecules, and then we made this shell the polycatechol-amine, that is the catechol-based material for the tissue adhesiveness. So when we make the granular structure, we can get the adhesive characteristics by this shell, and we can also make the hydrogel, and this shell has also the conductivity by the compressionation reaction. That is simply the oxidation and reduction properties of the catechol materials. Because of this granular structure, when we inject this material on the skin, the sweat or air or heat can be dissipated by the skin. And then that granular structure has the high sensitivity that is very effective for the human motion sensing. So using this hydrogel, we would like to demonstrate use them as the strain sensor. So first of all, we made the core material, the hyaluronic acid, and this hyaluronic acid can be photocross-linked. So we partially cross-link the polymer as a bulk-type material, and then we inject under the mesh, like the micro-sized mesh, and then we simply fragment the bulk hydrogel to the granular structure, which is called the hydropellet. After that, we can get the granular structures. After then, we coat that granules using the polydopamine for the tissue adhesiveness. So this is the brown colored hydrogel with the adhesiveness and printability and conductivity as well. So we also check the conductivity like here. So resistance like here. It is not so high value, but it is enough for the sensing of the human motion. So using this hydrogel as a strain sensor, we print that hydrogel on the finger. Like here, you cannot see well, but there is hydrogels on the finger. So we check the hydrogel capability for the finger motion sensing, and then we connect this robotic arm for writing some letters using based on the hydrogel materials. We also check this strain sensor capability for the metal bus interfacing. So that's the same principles, but we can also use the hydrogel material for the metaverse interfacing. So that is a kind of the unique demonstration of the hydrogels as a strain sensor, I think. So this will be the last topic. Almost 30 minutes left, but okay. So this will be the last topic for my talk. I will more focus on the peripheral nerve injury and treatment of them. What kind of peripheral nerve injury can occur in general settings? So when in an accident or in a genetic disorder or some trauma cases, the people can have the injury in their nerve. In that case, the medical doctors simply cut or the transect nerve, and then they need to connect the nerve using the sutures. But the suture method takes a long operation time. So also, the medical doctors needs the expertise for the microsurgical skill to connect single nerve. So these skills also affecting the recovery of the muscle tissues of the patient. So our research is for overcoming this stirring method. So using this sticky patch, we can achieve the nerve connection within just 1 minute. What is the difference from this stirs and sticky patch? So you can see here the suturing is very complicated. So for single nerve connection, it will take almost 600 seconds, 13 minutes for one nerve. So, but if we use this sticky patch, it is only 1 minute. So we can demonstrate this efficacy of our hydrogel-based patch for the rat sciatic nerve model, and monkey median nerve model. So our patches here is a very transparent, but they are having the different hierarchical structure that is inspired by the human skin tissue. So our skin tissue has the 3 layers, like the epidermis, dermis, and hypodermis. So the last hypodermis layer has a very softness, and the epidermis has the elasticity compared to this hypodermis. That means our skin has a mechanically gradient structures. So mimicking these structures, we set up our hydrogel. The first layer is the elastic silicone-based polymer, and second one is also silicone-based polymer, but with the medium mechanical modulus. And the last one is our adhesive hydrogel, as I mentioned in the previous slide. So using this hydrogel, we firstly checked the adhesive strength of our patch. So simply, our adhesive polymer is here, the arginate-based polymer conjugated with the phenylborate, and the elastic polymer is here, that is the self-healing polymer with multiple hydrogen bonds. So during the adhesive procedure of our patch, that self-healing polymers can support mechanically for the adhesive hydrogels. The hydrogel has the relatively very soft material compared to the elastic polymers. Anyway, so our patches here, they are having the different and the very strong adhesive strength compared to the conventionally used medical glue materials. And then we also check the feasibility of our patch in the nerve model. The first video is showing the micro stirring. So the Korean orthopedic doctors try to connect the nerve tissue, the single nerve tissue. It takes 13 minutes for one nerve connection. But if we use this transparent patch, all procedures involves simply the nerve is applied on the patch and then wrapping and cutting. That's all process for the nerve connection. And it takes just 1 minute. This is the rat sciatic nerve model. So they are having the 2 millimeter or 2.5 millimeter for the diameter. So we also check the feasibility of our patch in the monkey nerve model. So we made the wide patch like here. And then we also apply the nerve on the patch and then wrapping in the same manner with the rat sciatic nerve model. That's all process for the operation. So this is also it takes also within the 1 minute for the single nerve connections. So in this case, that nerve is the median nerve, but that type of the nerve, when the nerve is damaged, we cannot use some muscles. So after the recovery, we check some motion, some muscle, the movement by this animal. At the 1 month after the implantation of our patch, the monkey could not grip the small snacks positioned in the small box. So there is the 9 snacks in the box, but he cannot grip all snacks. He has the failure for gripping, the catching it. But that is a one month situation. But after the 12 months, he could get the all snacks, like here. So that means his nerve is recovered fully after the implantation of our patch, and actually our patch has the similar recovery level compared to the suture. So the time to gripping the snacks is the reaching to the normal range at the 1 year, and then EMG signal is also recovered to the 60% of the initial level at the 12 months. And then we also check the histological analysis comparing the suturing method and the patch method that all shows the similar recovery for the nerve anatomy. So that is very sad news for us. So we would like to find the benefit of our patch about the electronics field. So as I mentioned it, so we have the 3 different layers of our patch. So the upper layer is the elastomer, the silicone-based polymer, so we can set up the electrode on the patch. So if we use the electronic patch and the adhesive patch, we can simply seal our nerve, and then we can also stimulate the electrically for the nerve regeneration, for enhancing the nerve regeneration. So you can see here, so using our patch, we can stimulate the nerve tissues, and we can also find the thumb muscle movement like here. So using this electronic-based method, we are still conducting the experiment for the enhanced nerve repair. Also, we can encapsulate some of the therapeutic molecules on the adhesive hydrogel layer. So in this case, we encapsulate the nerve growth factors for the enhanced nerve repair. And then we also check the release profile of the therapeutic molecule from our patch material. And then we also check the recovery time scale compared to the suturing and patch without nerve growth factors. So you can see here, this one, and this one. At the 4-week, that's the initial stage of the nerve recovery, our patch with the nerve growth factor can show the better recovery compared to the suturing or patch without nerve growth factors. So from this result, we can think about our hydrogel-based patch can be a therapeutic reservoir for the conventional drug systems. So that is one of the advantages for our patch materials. Okay, so in summary, we are using the adhesive moieties catechol color like the polyphenol and phenylborate molecules for the conjugating to the natural polymers. Using that adhesive polymers, we can make the conductive and injectable hydrogel like these 2 studies, and then we also use that material as a coating material for the patch and electronics for getting the peripheral nerve repair. Okay, this is my lab members, and thank you for my collaborators, and thank you for your attention.